So let me start with a brief recapitulation. So to talk about, so this was what I called third characterization of the ellipse. So if you want to understand an ellipse with foci at f prime and with diameter 2a, what you did was to draw a circle delta of radius 2a with center at f, and then what you did was to draw circles which incided in the second focus f prime and touched the circle delta. The centers of such circles, well, there are infinite many of them, will constitute an ellipse of foci f prime and great diameter 2a. Okay, so we talked at length about this, why this is true, so on and so forth. And there was one point where I made the allusion that how does one draw the circle psi, which goes through f prime and touches the big circle delta in M? Well, the basic construction is take the point of tangency M, take the point of contact M, and of course the center of the circle psi will be on the line FM, so you draw the line FM, and then of course the center of the circle psi will also be on the perpendicular bisector of the line segment f prime M. So let the perpendicular bisector of f prime M intersect the line FM, the point X, the center of the circle, which goes through f prime and touches delta in M. Right, so that's what. So you can repeat this construction for all sorts of M's, and the center actually describes an ellipse. And all the while, this famous, okay, so I made the allusion that this line segment, this perpendicular bisector of the line segment f prime M has a special role to play. It is in fact the line T, the perpendicular bisector of the line segment f prime M. The line T is in fact the tangent to the ellipse at the point X. Okay, and you can have similar observations. You can make similar observations, and you can prove them for hyperbolas and parabolas, so on and so forth. Now, why is this true? Why is this true? I would like to give you a proof of this state of affairs, why the line T is tangent to the ellipse. Now, let me first of all clarify what it is when we talk about the tangent to an ellipse. It's quite simply. So perhaps I should start here. Şuraya gelebilir miyiz? Okay, so what do we mean, first of all? So in the presence of an ellipse, so this is an ellipse, let's say, okay, and you have got a point X on it. What do we mean when we talk about the tangent at X? Well, what is meant is quite simple. You simply take another point, Y, on the ellipse, and you look at the chord xy, okay? That's the line that joins x and y. And while leaving x fixed, if you let y approach x, of course, this straight line xy will occupy a limiting position, and that is the tangent line at x. Okay, so let's say this is the line xy, and as y moves towards x, xy will move towards the tangent line at t. So okay, so the tangent line, so let me write it down. The tangent line at x is the limiting position of the chord xy as y approaches x. Okay, so that's all that there is to it. Okay, so now let's apply this idea. Okay, so I would like to show you that indeed in an ellipse with foci f and f prime, and if I take a point x, fixed point x, the tangent at x will in fact be exact the perpendicular bisector of the line segment f prime m. Now, so I would like to draw a new. Okay, so I must make a rather big picture. There are a few things which are okay. So why is this the case? Okay. So let's say proposition. The notation and terminology is as stated above. So the tangent line, the perpendicular bisector. The perpendicular bisector of the line segment f prime m is, if you like, this is the t, is the tangent at x. Okay. So I don't need to explain the notation and the terminology. It's all there. Okay. So let's do it. Why is that? Well, okay. So let me start with the directrix circle. I'm not going to draw the whole circle. So it's a rather biggish affair. Okay. So that's the directrix circle delta. Okay, as on this picture. Its center, well, more or less here, is f. So I will take a fixed point x, and I will take a point y, which I shall imagine to be variable and approaching x. So how do I do it? Well, I simply take a point m. Okay, so let me use. So I want to be consistent. So so I'll take a point m to construct my, okay, so where is f prime? F prime is somewhere here. Okay, that's the second focus. Okay, so let me take an m here. And so let's construct the circle psi. So I join f and m, and I take the perpendicular bisector. Well, this is going to be important. Okay, the perpendicular bisector of f prime m. So this is the point. This is the point where the center of the circle, this interesting circle is. Well, let's call it x. So this is going to be our point x here, and I shall treat it as a fixed point. And the circle that goes through f prime and touches the delta, the directrix circle at m is, now we can draw it very easily. Okay, right. So that's, it's a little difficult to do it on the blackboard. So yeah, there it is. We are done. Now let's take a second point y. Okay, and I shall let y approach x. Okay, so what happens is the following. So how do you do it? Well, you simply take another point n. Okay, like this. Let me take it a little further down so that I can obtain a nice picture. And okay, so how do I draw the circle that goes through f prime and touches the big circle delta in n? Well, that's the usual thing. So I take the line actually, not the line segment, fn. Okay, and I consider the line segment f prime n. Okay, and okay, so let's call this first circle psi. Don't let me forget that. Okay, and then I take the perpendicular bisector of f prime n to obtain. Okay, there it is. To obtain the point y. Okay, so that's x. That's y. Check that. You don't need that. You don't need that. But you can imagine that the ellipse is something like this. I mean, if you require that kind of help. Okay, so that's how the ellipse is sitting here. Okay, so just as in this picture. Right. So that's the thing. That's the thing. And so let me use a little bit of color to indicate this straight line. That's important for us. The straight line, which is the perpendicular bisector of f m prime. That's t. So what I want is to show that actually the chord. Okay, so let me use a little bit of color there. So this chord. Okay, so I have not given any color to this chord. The chord xy, so it is something like this. Okay, the chord xy. I will show you that as y approaches x, the chord xy will have the limiting position t. That's the perpendicular bisector of the line segment f prime m. So let me use, to get a consistent picture, let me indicate my foci in blue. Good. So there it is. So why will that happen? Why will that happen? Okay, perhaps now I should indicate. Okay, so perhaps now I shall indicate. Now that's the part where the thing gets a little bit complicated. Not too complicated actually. So let me draw. Okay, so this is the circle psi that goes through f prime, touches the big circle delta in M. So that's it. And let me draw the other circle that has a center at y, passes through f prime and touches the big circle at n. So that is somewhat delicate. So okay, something like this. Okay, yeah, I'm doing pretty well, I guess. Yeah, not too bad. I don't need the whole circle actually, but okay, here we are. So let's call this circle eta. Eta is the circle with its center at y. Have I got it right? No, that's bad. That's actually a rather large circle. Okay, yeah, that's right. Okay, right, okay. Now there is something interesting happening, I don't know. I mean, I did tell you that if you take the two circles, then the two non-concentric circles, the radical axis is a straight line which is perpendicular to the line joining the centers. And of course, there are some special cases. For instance, if the two circles intersect, well, that line must of necessity be the common chord. That's quite clear. If, furthermore, if your circles touch one another, like this, let's say, then the radical axis will actually be the common tangent. Well, so now let's observe the following facts. The big circle and the circle eta has radical axis which is the tangent to delta at n. Okay? And the big circle delta and the circle, tangent circle psi, which I keep fixed, has a radical axis which is the tangent line to delta at m. And they intersect, of course, in some points, k. And, well, what can you say about k? You see, k is on the radical axis of delta and eta. It's also on the radical axis of delta and psi. So this is the radical center of the circles psi, eta, and delta. Right. So, well, that's rather exciting. Well, that means, of course, this is where the accuracy of your drawings come into question. Okay, so that's the circle eta with center y. And this is the circle psi with center x. And of course, so that means, so this k, since it's the radical center of psi, eta, and delta, it is also on the radical axis of, okay, so let me get rid of this stuff. For is my so let's get rid of this whole stuff. So it means that therefore k is on the radical axis of psi and eta. Now let's look at what that radical axis is. The circles psi and eta intersect in some point. Let me call that L. Okay? So, which is, this radical axis is therefore the line f prime L. Well, our theorem is saying that if I join f prime and L, then it must go through k. Therefore, k lies on, okay, so show that problem. F prime, L, K are collinear. Now, what's so exciting about this? Well, exciting is the following. When you want y to move on the ellipse, well, I don't want to draw it, but it helps, you know. It's when you're doing this kind of geometry, it's nice to be able to go on without drawing the conic sections, but well, it helps too. Anyhow, okay, so when you let y approach x when you let y move on the ellipse and approach the point x, well, that means the point n is moving towards m. Okay, so actually you can simply say let n move towards m. When that happens, when n moves towards m, then look at these 3 points. The points, 4 points. The points n, m, k, and l merge together. So as y approaches x, the points n, l, did I say n? M, k, l merge into a single point. Merge into which point? Well, check that, I don't know. But x is fixed, so I take m to be fixed. M is fixed. So I think it would be wise to, and of course everything else is moving. When you let n move towards m, or equivalent to when you let y move towards x, everything except m, of course, and x, and of course t, is moving. So n, k, and l move into m. But you see, since k is on the, since f prime l k are collinear, but this is not all. The radical axis f prime l of psi and eta. Psi has center x, eta has center y. This is the line which is radical axis, and therefore I know that, but f prime l, being the radical axis, is always perpendicular to x. I mean, xy is the radical axis. Just a minute. Yeah. xy, okay, so xy is the line that joins the centers, f prime l is the radical axis, so f prime l is always perpendicular to xy. So you see what happens. L merges into m, So this becomes f prime m, the line segment, in fact, and that is perpendicular to the limiting position that this occupies, t. So it must be t. So this must be t. So the limiting position. So we conclude that the line xy actually moves into the line segment into the t into t, which is the perpendicular bisector of f prime m. F prime m. Right. So that's actually I can make this a little bit clearer. I can make this a little clearer. Let me make it a little clearer. Actually, you see, xy is the line that joins the centers of psi and eta. F prime L is the radical axis. Okay. So well, I don't need to say it's the common chord, but I know that xy is the perpendicular bisector of f prime L. So xy is the perpendicular bisector of f prime L. So it means that L moves into M, so f prime L moves in fact into f prime M. So that means xy has to occupy the limiting position T, which is the perpendicular bisector, of f prime M. Okay, so there we are. That is why this significant line T is in fact the tangent line at the point X. Okay, şimdi çocuklar, yeah, so that's the main idea. That's the main idea. And of course, you will go home and you will try to replicate my arguments. It's a good idea. An even better idea would be to replicate this proposition, state and prove. The above result for a hyperbola. This will be, in fact, much more instructive than going through my arguments. Of course, I think you should have a very clear idea of what's going on in the ellipse case. To solve the hyperbola case, there's no problem. The parabola situation requires a little bit more attention. In the case of the parabola, actually, the obvious thing happens, but once again, you have to, okay, so in the case of the parabola, the directrix circle is replaced by the directrix line, okay, and you have got, of course, one focus, F, okay, so let me look at the perpendicular that's dropped from F onto the directrix, that's the so-called axis of the parabola, and okay, so of course we have the very same constructions, and in this case, however, what happens is, okay, so let us start with a point M on the directrix. So if you want to construct a circle that goes through F and touches the directrix at M, then all you have to do is to draw a perpendicular to the directrix at M. This replaces in the limiting form, this replaces the line FM, which is the radius through M. Well, you can imagine this focus at infinity. Anyhow, and then you join M and F, and you take the perpendicular bisector. So let me indicate that in green. So that's the line T. Okay, and that line T intersects this horizontal line, the perpendicular at M. Okay, that's the point X. Okay, so okay, so that's the line T. So as you move M on the directrix line, the point X will of course describe a parabola, and that parabola will be of course tangent to the straight line T, which is the perpendicular bisector of Fm. So there we are. So that's the thing. Okay, I want you to, once again, this too, I would like to leave to the student, left to the student. So I want you to actually to establish that for every m, the point X constructed in this manner. How? By drawing the by erecting the perpendicular to the directrix at M and letting it intersect with the perpendicular bisector of the line segment Fm at X. That's a point, and the tangent, and to show that the tangent line at X is actually the perpendicular bisector of the line segment Fm. Right. So this takes care of the whole situation. I've done ellipse, I've done hyperbola, I've done the ellipse, although I have left some of the work to you. Right. So this allows us to talk about the tangent lines as well as points on conic sections. And in my next lecture, I'm stopping now. In my next lecture, I shall talk about two very important and classical results on the tangent lines to conic sections in general. And I shall pursue the same method. I shall present the result for an ellipse, and I shall strongly advise you to go home and replicate my results on the hyperbola and on the parabola. That is, however, in my next lecture.